Hi everyone, welcome to Serving Machine Learning Models as an Inference API in Production. My name is Marc. I have a background in computer science as well as in computational neuroscience. And in the past, I founded my own company, a software agency here in Hamburg, and grew to about 25 people. But recently, I joined a startup called MindPeak. And at MindPeak, our mission is to increase cancer diagnostic accuracy and make it accessible to everyone who is in need. And why is this such an important thing? Well, we're in the field of pathology, and don't get me wrong, pathology is not about dead people. I mean, it is in small parts as well, but pathology is also about analyzing cells of people and analyzing whether they have cancer or what types of cancer. And it's a pressing demand because luckily, we managed that people can get older and older now because we cured a lot of other diseases. But that means we still have a lot of cancer cases, and they're actually increasing. And so more and more cancer cases need to be analyzed. But the problem with this is that the pathologists, they stay roughly the same because sometimes the older ones get out of their jobs and the newer ones come, but so the number is roughly equivalent. And what that means is that we have more cases for the same amount of people, so they need to work a lot more or faster. And if they work the same amount of hours and just make more cases, then research has found out that their accuracy is actually worse, so they make more mistakes. And I think no one here of us wants to have mistakes in their cancer diagnosis, right? And so what we're trying to do is we try to build automation tools for visual diagnosis in pathology. And we do that using deep learning. And our tools are then used by these doctors, these pathologists, to help them make more reliable and faster diagnosis. And here you can see how these images look like roughly. They're fully anonymized images. And just to get you into the workflow, how this works in this field. So if someone goes to the doctor and there's a suspicion that they might have cancer, say breast cancer or lung cancer. Of course, first there are many methods the doctor can use to figure that out as good as possible, but at some point, usually a biopsy is taken, so a small piece of tissue is taken from the body, and that is then sent to a pathology lab. And the pathologist prepares this piece of tissue, so it's this weird-looking thing here, slices it into small pieces and puts it into little glass slides. You maybe know them from your biology classes back in school when you look at things under a microscope. And that's what they do with these tissue types. So they examine it under, say, 20 or 40 times magnification. And then what they see looks something like this. And from that, they infer what is the actual state. So how severe is the tumor? Is it fast growing? And based on that, they also provide suggestions for treatments. So that they send back to the initial doctor that sent in this biopsy a recommendation how the patient should be treated in the future. That could be, should he have an operation? Should he get chemotherapy? Something like that. So the diagnosis of the pathologist is actually very, very important because it sets the ground truth for the patient's well-being. And this is how we envision it for the future. So instead of using microscopes, we could have scanners that actually digitize these tissue types. And then an AI can pre-analyze them and rate them according to the severity. And so the pathologist can then kind of check on the screen and have a pre-sorted urgency backlog, so to say, and can then still make the final decision on the treatment and thereby improving the model further on. But we're not totally there yet. The field is undergoing digitization, but getting AI into it is still a long way to go. But we're making good progress right now. So let's get started for today with training a deep learning model. And this is roughly the life cycle you usually have when training a deep learning model. First, of course, we need to get some data. In our case, that means scanning data with these scanners. Or there are also microscope cameras that you kind of plug onto a microscope and they can take pictures. So this is what we do, and then we annotate the data, because in the medicine field, data is always scarce, I would say. So it's really important that you have yourself a good annotation pipeline where you annotate your data. We have a lot of medical students that do pre-annotation, then have pathologists that check on it and verify the results. And then when you have your data together, you, of course, train your model, and using a train and validation set. And once that's trained well enough, you evaluate on your test set. And if that is good, then you go ahead and deploy this stuff. Now afterwards, once it's deployed, you need to monitor, check if everything is going according to your plan and everything works. And based on the monitoring evaluation, you probably collect further data and then repeat the whole cycle. And today, we're focusing here on the deployment part. So this will be our example case here. This is our first product that we put out into the wild now. It's cancer cell detection. So what we get as an input are images like these. And the goal of the model is to detect all these individual little cells and also classify them. So this is what is indicated here. I won't go into the details now. It's not relevant for the talk, but depending on the classes detected, we show several different colors. Is it a tumor cell, a non-tumor cell, stuff like that. And the pathologist then gets this visualization and can verify if it's good. And then that helps him make the task in seconds instead of minutes. Now, why is deep learning very appropriate here? As you can see, these images come in a big variety. So depending on the lab that prepares the slide, depending on the scanner, you have many different things. For example, if you look at this thing here, it's very dark. This is because it's a microscope camera, and they have usually bad quality. And then others are much lighter, or even some are brownish, some are blackish. And our model needs to take care of all these variances. So it can do that, that's good. So we built a cool model, and now the question is, how can we get this out? How can we serve this as an API? And our goal for this was to have the image being sent to this API and then return a JSON response. The JSON response would encode the location of the different cells, where they are, and which classes they are. And so our first thought was, well, let's go with the serverless Lambda function approach. So we will send the image to a Lambda function and then get the JSON response. So serverless Lambda function, that means not that there are no servers involved, but here we tried it with AWS. So AWS is taking care of the server side. And you as a developer basically focus on putting your code out there. And then when people call it, AWS puts the code on some server, calculates the result, and gives you back the result. So that's pretty cool because, first of all, you can do this very quickly. I mean, you don't need to take care of much. You just need to build your code, put it in a function, and then you're more or less good to go. So your time to market is really, really short. You can experiment really quickly. And for us as a startup, that's really cool because you can just try it out fast and get into the market as soon as possible. Then you don't need to maintain any servers. It's also good. So you need less people involved with it. You don't need a system admin who can take care of all the security aspects of maintaining servers and so forth. There's also scalability inbuilt. So with serverless functions, AWS basically says, and there are also other cloud providers, of course, that do the similar things. Okay, give me your code, and however many people call it, we will just scale it to more servers, and then it will scale out of the box. And the fourth good thing is cost efficiency, because you only pay for what you use. So if many people use your API, you pay more. If no one uses it, you pay nothing. But it's not always sunny. There's, of course, problems with this approach. So on serverless AWS functions, you cannot use GPUs, and in deep learning, we often use GPUs. But for inference, you might not need a GPU, so that really depends on the use case. Lambda functions are also heavily restricted. For example, you can only upload, so your whole code with all your dependencies cannot be more than 250 megabytes. And also in terms of the computation power, I think 3 gigabytes of RAM, something like that, is the maximum a function can use. Then we have the cold start problem, which is that AWS somehow needs to provision your function. So it needs to put it somewhere so it can be executed. And if someone hasn't called your function in a long time, of course, Amazon wants to save costs, so they kind of turn it down. And then if another call is coming in, they need to spin it up, and that takes startup time. And this is called the cold start problem, because the initial cold calls always take longer than when the function is already on some server and hot. Yeah, fourth disadvantage is vendor lock-in. You can just debate and discuss. I mean, there are many different things to discuss here. But of course, if you put stuff and are dependent on AWS and they raise the price for Lambda functions in the future, you might need to move to some other provider or something, so you have some lock-in effect. Cool. So given the size restriction, that's actually a problem, because PyTorch, we use PyTorch for training the deep learning, and it comes with a big bundle nowadays. So putting it into 250 megabytes is a challenge. And what's a cool possibility are Lambda layers. So Lambda layers just, I mean, most of you probably know Docker is like a virtual layer where you can put code, and then you can reuse that layer in many different functions. So I thought, well, let's just build a Lambda layer with PyTorch in it. This is roughly here the steps. So you build a virtual environment, activate it, pip install all your packages, then zip it up, upload it to some S3 bucket, and create it as a Lambda layer, and then in your function you can actually use it. Well, done, said, we did that, but be aware of the dangerous snake, because actually all your deployment package also includes all the layers, so the 250 megabytes is still the limit, and you're still not above that. So we need to employ some magic. There's a trick called the temp extraction method, and that is actually also very simple. So you create a helper script that creates a folder in your temp file system, because in the temp file system in AWS Lambda you can have 512 megabytes. So you add a folder there, you unzip your dependencies there, you add it to the Python path, and then in your actual Lambda function script, you just use that helper script to do that when the function is run. So that adds a little bit of overhead in terms of startup time, but then you can use more than the 250 megabytes. And that is actually enough to get PyTorch on it. So we'll demonstrate this in a small demo. And the way we do this is we have our model weights on S3, and then the Lambda function basically just downloads the model weights and initializes the traced model. So in PyTorch you can trace your model. That just means that it optimizes it, so you don't need to include all your classes and all your source code that you build it with. You just need the model weights and you can just use it. And the cool thing is, in this approach, when you retrain your model and upload newer weights, then you don't need to change your function code, because it will just download the newest weights and then serve that function. And of course, we use the Lambda layer that actually enables us to use PyTorch and all the dependencies. So in code, this looks roughly like this. It's just a download with the S3 helper. Then you unzip that, put it to some temp folder, and then you make your inference function in PyTorch as you used to. All right, so let's check it out. So in this demo, I use SAM, the serverless application model of AWS. You can use it to also locally test your Lambda functions, so I don't need to actually use an online Lambda function here. So you provision your stuff in a YAML file, and we have the S3 bucket where we put our model. We have our model, which is just the zipped up weights, and then we have this. This is the Lambda function, the image predict function. Is it readable or? Yes.
Yes.
Okay. And here we just say, okay, we have a folder called PyTorch, and inside we have a file called run inference, and there we should execute the Lambda handler function. And then there are some settings like memory and so forth, which is not so relevant. And we have the Lambda layer that I talked about before. This contains the PyTorch with our dependencies. And then we tell it, okay, we want to have it as an API on the path image classification, where we can send a post request. So I'll start that up, and that means now locally running on port 3000, we have this API set up, and that would be the same when we deploy it. We would have it as a Lambda function, and it would be the similar thing. And here, to demonstrate, I made a little script, which is just calling this URL and posting an image there. The image I can just give it here. Now we can see when I start that, it will actually check out the Lambda layer. It says, all right, I already have it, so I can skip it, and then it checks the credentials, downloads the model, says the S3 bucket is MindPeak Chi67, it finds the model, puts it to the temp folder, and so forth, and then finally does the inference, and this took around 4 seconds here. Now let's check out which image I sent. Oh yeah, and here's the result, of course. It's the JSON response that we calculated. Of course, it doesn't tell you much because it's just numbers. This is coordinates relative to the image. Later on, we will see what this means. So this is the image I sent, a small patch of cells. And now you can already maybe guess, this already took 4 seconds here. And for our practical case, we need much bigger images. So it gets really unfeasible. We need images that are maybe 1000 times 1000 pixels in size. And then in that case, Lambda is just too slow. And that's exactly because you cannot use a GPU here, and we actually need a GPU. I also built this with a CFAR. You maybe know this, just an image classification task. So if you're interested in checking this out yourself, this is on GitHub, because I cannot share the MindPeak cell detection code, but this is like a dummy wrapper doing the same stuff. Okay, so what are our next options? So we need GPUs, and I thought, well, maybe it's cool that we use Docker with GPUs, because when we need GPU servers, how do we provision them? How can we handle with them? So we replace AWS Lambda with a Docker container. So what's the good thing here? Well, first off, we can use a GPU. That's the obvious one. Second off, we are free from our dependencies. By that, I mean, on the server, we don't need to install all the packages and stuff because we specify that in Docker. So if we set up several servers, we don't need to repeat ourselves and deal with that. This is also great for having the same environment. So you can use the Docker container in your dev setup. You can develop locally. You can very well use it for continuous integration, continuous deployment. And when you share it with colleagues, there's no discussion of which package do you have here and there. The provisioning is very quick with Docker, so because it reuses the operating system and just puts the layers on top, is very quick to start it up. And yeah, it gives you everything that you really need to get up and running. But of course, it has some disadvantages. There is an overhead, so if you use Docker, it sets up their own network layers, and of course the inference will have a little bit of an additional time in the order of, let's say something like 50 milliseconds or so. Then you have rising complexity. So, of course, when you put Docker into your stack, you need to deal with Docker as well. You need to know how it works. Your tech team needs to be able to deal with it, to put everything together and have a solution that is stable. You need servers, or at least somewhere where Docker can be running. So then you need to deal with the server admin stuff again. Not what everyone is happy about. And last but not least, when I said freedom from packages, not totally true. So there's actually dependencies on the NVIDIA drivers. So we use NVIDIA GPUs, and actually it turns out that Docker needs to be aware of what NVIDIA drivers are running on your machine. So it's not totally agnostic. You cannot put it on any machine with any GPU, but you need to take care of this. But there is lots of help from NVIDIA. They actually build Docker images, and that's really cool. I mean, I was surprised that it worked that well out of the box. So, for example, for us, there are many different images, but as we wanted to use PyTorch, they have a Docker image where there's PyTorch inside, or the CUDA drivers needed for that, and you can more or less just use it. However, you need to make sure that your drivers have the right version, as I said before. So to do that, you can check the NVIDIA SMI client tool, and it shows you then your version number. And when you check this link here, then NVIDIA says which Docker image needs which version. So that you need to take into account. And that's a bit annoying, but I mean, you just need to figure out which version can you use on your servers, and then you're good to go. But we also need to make sure that Docker can actually access the GPU. And before version 1903, that was not possible natively. And in that case, you needed a package called NVIDIA Docker 2 that kind of replaced Docker. So it's like a binary that runs instead of Docker and enriches Docker with the access to GPUs. But good news, since 1903, Docker supports GPUs natively. There are a few caveats. Currently, if you use Docker Compose, the Docker Compose file reference is not as up to date. So in Docker Compose, you cannot specify GPUs yet, so that's a bummer. There's an issue you can check out here. I think it will catch up soon, but at least for now, it doesn't work like that. You can still use NVIDIA Docker 2 and get around that problem. We had the earlier version first, and we migrated to Docker 1903, and that worked rather well. It's a bit confusing to set it up sometimes to get the NVIDIA runtime as the default runtime, but besides, I didn't have any big problems. Okay, so this is what the inference architecture looks like in this Docker scenario. We have a request coming in, and that hits Nginx as our web server. And then Nginx forwards it to gUnicorn, which is serving Flask with PyTorch. And again, we use the traced model inside PyTorch to have it as lean as possible. And just as a quick code overview for Flask, so it's very easy to do something like that. You just say, okay, I have a request and I get the image. The image is read, and you open it, for example, with pill, and then you pass it into your inference function. And then you get the result from the model, and then you can JSONize it and return it to the user. Okay, so let's have a look at that. So I'm now connected on some server that has a GPU because I don't have one in my laptop. So you can see there are two containers here. One is for Nginx, running on port 8001, and one is for our API that is executing gUnicorn, which is calling in turn the Flask application with our PyTorch model. And here, similarly to in the AWS Lambda case, there's a little script which is able to call this URL. It basically just opens the image and puts it as a payload with some headers and uses the request library to post it to this API URL. And then we get the JSON response and output it. So let me start this up here. So you can see that it was very quick to spin something up. Now I send an image which has around, it says it somewhere here, 776 times 872. And you can see it took a while, took about, what does it say, 9.8 seconds, the inference. So that's still quite long. And we might wonder, is this enough? But if I resend it now, you can see that it runs in under a second. And this is because we use something called calibration. So you can tell PyTorch that it calibrates according to the image size. So when it encounters an image size the first time, it kind of calculates what are the best operations to do, in this case, for my machine architecture. And then when it gets the image size another time, it's much faster. I mean, this is just a demo. Of course, in our live system, we do the calibration up front to several image sizes, and then you can be sure that you have a quick response. So I promised that I show you what this looks like. So we built this as a little web demo here. So this is the exact picture I just put in there, so that you see how the JSON response is actually represented. And you can see that it's rather quick. So this was the input image, and then now we get all the result back, and the JSON response is now visualized as these little dots. And what is really important for the pathologist here is that we count these cells and then calculate a score out of it, because that's really annoying work for the pathologist. Usually he needs to manually count, then calculate the score, and he really doesn't want to do that so much. So because he doesn't want to count, he usually just estimates it and feels bad about it because it's not really according to the clinical requirements. Yeah, also there's example code for this Docker thing. If you want to check it out, it's on my GitHub. I also built it with the CFAR image classification model, so you can check it out if you want to build something like that. Now, this was just a very brief overview of the main building parts. In the real world, of course, we have a lot more complexity, so what I would recommend to put in the front is an API gateway that helps you protect you from some attacks. It can help you with throttling requests if someone is spamming you, or it can also help you in authenticating and authorizing your users. You need to think about inference speed. So I briefly talked about the calibration stuff, but there's also more you can do. For example, we try to get rid of everything that's not really relevant to the response to the user and asynchronously process that. For example, you might need to collect some metrics that you want to visualize, stuff like that. You can do that asynchronously. Of course, you need to take a lot of care for stability, security. You need to write tests with it. You need to integrate that into your CI/CD system. We use GitLab for that. That works really well with Docker. And you need to encrypt your whole pathway through your API gateway and so forth with SSL, obviously. Of course, you want to monitor what's going on. If you get any errors, you want to be notified. And you really want to see how things play out, how things are developing. So you really should collect metrics and show them. For example, we use a Grafana dashboard in our office where we can always see what kind of requests are coming in, how long are the requests taking. And that's really, really useful. We had one case in the beginning where our post-processing had a bug. And if there were many cells detected, then actually the post-processing was much slower than the actual inference of the model. And we could see that in our metrics, and then we fixed the bug, and then it was a much faster experience for our users. And what we also did recently is to scale over multiple servers, because if you have a server with one GPU and that GPU is processing, then of course that's a big bottleneck. So we are using Docker Swarm to scale over several servers with GPUs. Yeah, this is roughly how our API architecture looks like right now. So requests get into the API gateway of AWS. We then have several GPU servers running. And on them, we have Docker Swarm that I can really recommend. It's a really cool tool. With Traffic, it's a great combination that uses Let's Encrypt to automatically provision your SSL certificates. It's really awesome. Uses Consul as the distributed certificate store. And then we have our PyTorch API here that uses the GPU. And we use asynchronous threads to store data like metrics and so forth. And for that, actually, we use Lambda functions again. So it wasn't all lost that we played around with Lambda functions initially, but at least we could still use it. Of course, these were just two options that I tried out with and had some good success in the end. There are many others. When you trace your PyTorch model, you could also use it in C++, which might be more efficient if you tried it out. There are a lot of model server solutions coming up nowadays. I recently read about Redis AI, which seems cool. So you can integrate your AI inference into your Redis. So if you're already using Redis in your systems, that might be a good thing to have a look at. You could also transform to Caffe 2 and use a framework which can serve that. Like also NVIDIA provides TensorRT that they claim is much more efficient with GPUs. I played around quickly with it. It was a bit complicated, but maybe that was me. If you're on Kubernetes, there's Kubeflow that I heard good things about. And you could also go fully cloud with things like AWS SageMaker. But in my opinion, at least if you have it for inference and long-term running, GPUs in the cloud are really expensive right now. So to sum up, there are many things to consider when you want to get your machine learning API online. First of all, time to market. You need to try out quick solutions. You need to be cost efficient, so you don't want to waste your money, of course. You need to be able to handle the complexity of solutions you're creating with your tech team, because if you just want to get a very complex stack and then no one understands and you have bugs and stuff, that's horrible. That's a reason why we, for example, decided against Kubernetes and use Docker Swarm instead, because it's much easier to set up when you have a small team. Then you need to think about scalability. Of course, you don't want to prematurely optimize your code, but you want to think about, well, how many users will I have? When will I scale? How many requests do I expect? And inference speed is a very important factor as well. So it could be, for some use cases, you might be fine with having a response of like 5 minutes if if it's a process that runs and then the human looks at it later, that could be fine. So then you could your use case might change quite considerably. In our case, we wanted real-time responses, so the pathologist is sending the image, so he's sending a region, and he gets the response as soon as possible. When I set up the API gateway, over time, initially I had it in one endpoint with different deployment stages, but I found it was better to separate by environment, so we now have separate API gateways, one for dev, stage, and live. So if you're interested in that, you can talk to me later. If you have a use case that it's possible on the CPU, then I would really recommend to look into the serverless option. It's viable and it works really well, and you don't need to deal with a lot of other problems. So if that's the case, good. Otherwise, Docker on GPUs I found very good. You can look into model servers, and again, Docker Swarm is really nice. I'm really excited about it. And yeah, log and visualize your metrics. So of course, at MindPeak, we're looking for great colleagues. So if you're interested and are a developer or data scientist, contact me or write us at jobs@mindpeak.ai. And I reached the end of my presentation, and it's a lot of things to take in. So when you reach the end of your rope, tie a knot in it and hang on. Thanks. Any questions?
Can you tell us more about how you visualize your metrics? And also, do you measure something like data shift or something that can happen?
Sure. Visualizing metrics, yeah. So what we do is we basically log. So we have a Lambda function where we log a lot of metrics like how long did the inference take, what was the size of the image, how many cells did we find in the image. Yeah, stuff like that. So there's more probably, but basically KPIs that we think is relevant to the problem, things that might have an influence on results and speed. And then we write these results in a Postgres database and use Grafana here as a dashboard, and then we can have different visualizations for them. For the data shift, that's a very good question. Currently, we haven't done anything like that, but I'm sure we will do so in the future. Because currently, I mean, we're still starting out, so now we only have something like 50 requests per day, so it's not a very big concern right now, but of course, we continuously gather new data and retrain the model, so yeah.
Thanks for the great talk. I wonder if you considered, or what kind of model did you use firstly for this? And also, did you consider like pruning the model to make it smaller and faster, or use an alternative and so on?
Yeah, great question. So, yeah, I cannot tell very many details about the model, but I can tell you it's a fully convolutional architecture. So that's why we can put in any image sizes. At least as long as your GPU memory is playing along. That was actually another thing. I could talk about it, but I won't now. So, what was your second question?
If you prune the data.
Oh, pruning the data, yeah. That's a really interesting thing. Currently, we don't employ pruning itself. We have rather small models, so it's not like as big as ImageNet models usually are, stuff like that. So we try to keep it small, but we haven't employed pruning or stuff like that yet. But it's also something that we really want to try out.
Hey, two sets of questions. So the first one regarding all the Lambda stuff. So I know for a fact, because I did a lot of experience with that, experiments with that, that the last TensorFlow version, I mean, you're using PyTorch, but the last TensorFlow version that fits into a Lambda layer is 1.8, so it's ancient. Did you have similar problems, or what was eventually like the biggest problems you had? Like I ran into API gateway timeouts all the time and stuff like that. So what was the eventual reason for not choosing this way?
Yeah, so PyTorch in the newest version was able to be had in that, so we could use it as with the temp layer approach that worked. I'm not sure about, I haven't tried it out with TensorFlow, so I'm not sure about that. Problems, yeah, timeouts were problems we ran into as well, so especially API, if you use it in combination with API gateway, which is often the usual approach, API gateway has a hard timeout of 30 seconds. So if your request takes longer, you cannot get the response back. And that is a problem if you have longer running requests. You could get around that because the Lambda function actually can run longer that way. So what you could do is something like the Lambda function stores it somewhere, and then you need to poll later on and ask for the request, and then another Lambda function would get it from S3 or something like that. That would be viable. But for us, the main reason was it was just too slow because we had larger images and we needed a GPU. Yeah. that's why we decided against it.
All right, sure. So, like the second question is about, I mean, you mentioned other options. Like I see how like Google Cloud Functions or Azure Functions also wouldn't work for the same reasons, although they are less restrictive. But when you mentioned SageMaker, like the way I understand you're still using, I don't know, Docker or not, you're using GPU machines that have to be running somewhere. Like how exactly are you saving money there? I mean, like SageMaker is an expensive product, but you still have, I mean, you mentioned that GPUs on the cloud are expensive, but you have that, right?
Yeah, so the trick is we don't have GPUs with Amazon, but we have servers elsewhere. So they are like 7 times less expensive than on AWS.
Ah, yeah, cool, smart.
Thanks for the talk. Is the setup that you have, is it compatible with continuous deployment, and if not, how do you see going forward? Like if you realize that your model has problems and you have to take it and you have to replace it, how long does it take? And can you actually implement continuous deployment in there?
Oh yeah, it's we have it implemented. I mean, we don't we still manually click for the final deployments, but it's all in the GitLab CI pipeline. So we build images and then have a dev environment where we have CD completely automatically running, and then we put it on the stage environment, and if everything looks good, we click the button and then it's deployed. So that's why we use Docker Swarm, so we always have several instances running, and we do rolling updates. So one instance is shut down, a new model is starting up on some server, and then once it's tested and the health checks are working, then the next machine is replaced, and then at some point we have all new instances running.
So have you linked that monitoring that you talked about at the beginning, have you linked that to the deployment? So
Sorry.
if you've deployed your model, can you actually monitor it and trigger a replacement of it? If it goes wrong, if you see a metric going down, or...
Oh, so we haven't automatically, so we don't have anything automatic in place that if metrics go down, we replace something, but we could manually say, okay, make a rollback, and then it would work. Yeah.
Okay, cool, thanks.
Hi, thanks for your talk, and it's a very interesting topic because I'm also a software developer for medical software. How do you comply with medical software regulations? Like, how do you prove that your machine learning model doesn't provide or doesn't create false positives? Or, as the second part, how do you prove the security and safety of your quite complex tech stack?
Yes, that's a very good question and a very relevant one. So first of all, our system does not make decisions automatically, right? So we're just building support tools for the pathologist, and the pathologist is the one who's in control. So in the end, the final decision is always made by a human. So that kind of cuts down a little bit of a lot of concerns already. But we're also in the process of making clinical studies and getting a CE validation. So it's a regulatory framework to kind of fulfill all these requirements. Then you set up a quality control system and so forth.
So you're already on the market with your product, or not?
Yes, but currently it's called research use only. So in that case, if a lab wants to use it, they need to make a so-called self-validation. So they kind of evaluate your software and then kind of make a little in-house study. And they're used to do that because they do that for their own stainings and stuff as well.
Yeah, thanks.
Hi Mark, great talk actually. Do you run into shortage of data? Because has it happened that there is a scarcity of data for you to train?
Yeah, I mean, scarcity of data is horrible, and that's our biggest problem actually. So that's why we have many people working on actually labeling, annotating data, and getting all the data. So we collected a lot of data from many different labs and scanned the data with many different scanners to get all this variety in for that we need to learn in the field.
Okay.
But so currently we built our second product, and so we just start out right now. So we have a bunch of data collected, but of course it's not viable to make it as a product yet because we need much more data. So now we're in the process of collecting as much data until we have enough to prove that the metrics are actually good.
Okay, so and the life cycle that you show, then I believe that the data annotation part takes the most time, right?
Yes, that's correct. It's hard to see, but are there any other questions? All right. If you still have anything, just approach me afterwards, and thank you for listening.